Welcome to Energy Talks, a regular podcast series featuring expert discussions on power system testing, data management, cybersecurity, and important trends in the power industry. My name is Scott Williams from the podcast team at Omicron, and I will be your host. Hello, everyone. This is the fourth episode in our ongoing Energy Talks mini-series titled Experts Behind the Scenes in Power System Testing. This mini-series looks at the essential work happening backstage to ensure not only the reliability of electrical equipment, but also to shape the future of the electrical power industry. In previous episodes of this mini-series, I have spoken with a protection testing engineer, an applications engineer, and a software quality assurance engineer, all of whom are making important contributions to optimize power system testing. In this episode, I speak with a product manager who plays a vital role in balancing market demands with innovative research to develop testing methods and solutions that keep our power grids stable and reliable. My guest is Dr. Suruthi Chakraborty. Suruthi brings a fascinating perspective to the table as an Omicron product manager with a career that began in chemical engineering and has since spanned multiple continents and various areas of power system testing. Her work has been based on innovative thinking at a time of rapid digital transformation. Suruthi joins us to discuss, for example, the integration of digital twins and transformer condition assessments, more productive uses for artificial intelligence in power system testing, the challenges of a rapidly evolving power landscape, and the essential skills young engineers need to thrive amidst all of this change. So without further delay, I extend a warm welcome to Dr. Suruthi Chakraborty. Hi, Suruthi.
Hello, Scott, and thank you very much for having me today. How are you?
Very good, thank you. I'm pleased that you took the time to join us. Suruthi, please describe your journey so far in power system testing from your education to your current position.
Oh, wow. Yeah, that's a story of pure coincidence. So my background is in chemical engineering, and therefore arriving in power system testing was never part of the plan. So back in 2011, when I was doing my master's thesis at Crompton Greaves in India, and I was there as a working student, and I remember thinking, why on earth would a power transformer manufacturer need a chemical engineer in their labs? It just did not add up for me. And so the question stuck with me. So before my interview at Crompton Greaves, I was doing my preparatory research, and that's where I came across my first paper on moisture equilibrium in power transformers. Now, that sounds very niche for those who are in the field. But for me, that was the moment. Everything clicked. Suddenly, this massive piece of equipment that we call power transformers was no longer a static piece of device. It became something living for me, like a chemical reactor, where whatever is inside the insulation components, they are degrading. And their mechanism, this degradation mechanism, is basically determining whether this asset lives for years to come or it fails right now. And this shift in perspective, it completely had me hooked. So honestly, that fascination with power transformer condition monitoring never left me, no matter where I went. And it's also the motivation that drove me into my current position in product management. So stay curious and follow the questions that don't make sense yet, and let the real story unfold.
Okay, well, let's go for it. You've worked in India, Italy, Norway, and now Austria. What is one universal challenge in power system testing you've encountered across all these regions? And what is one unique regional difference that surprised you?
That's a big question and a good one. I think globally, power system testing industry always needs to be in synchronization with the evolving energy landscapes, new regulations, sustainability goals, and of course, digitalization. Therefore, the real challenge is always to find that sweet spot between market demands, customer requirements, and affordability. And I think this is universal, no matter where you go and in which part of the industry you are. But regionally speaking, I think there are quite many interesting examples. I have been very impressed with how Norway and the Nordic countries in general approach this. Their testing, monitoring, and diagnostic practices have evolved, and they have always evolved almost in lockstep with regulations. And therefore, the key players they are very quick to adapt as well. This creates this perfect environment for passionate innovation. And I think it was a very pleasant surprise and, of course, a great opportunity to work in this environment throughout my journey across the world.
I can imagine. Power system testing is often invisible to the public until something goes wrong. In your experience, Suruthi, what is the most misunderstood aspect of a testing expert's daily life?
Yeah, you're right there. Scott, from the outside, people often assume that testing experts are mainly involved when something falls, or they are mostly into analyzing faults, responding to outages, troubleshooting dramatic events, and so on. Whereas it's totally opposite. For a testing expert, the point is to ensure that nothing happens at all. And therefore, when it comes to overall evaluation of an expert's daily tasks, the painful process of meticulously reviewing and studying network configurations, anticipating edge cases, checking signals, or simulating faults and even documentation, it's mostly overlooked. I strongly believe that our testing experts are quietly preventing failures through this rigorous, detail oriented work with a very high level of expertise, discipline, and responsibility. And that's what is keeping the lights on.
After working in diverse academic and research environments across Europe, what motivated your move to a product-focused role at Omicron Electronics? And how does your research or background shape your approach as a product manager?
Oh, that's a very interesting question. Scott, I think that the basic difference between a product manager and a lab researcher is the former's capability, or let me say accessibility to the end users and the possibility to channel the feedback of the end users into direct product improvements. And that's a huge win for the researcher that lives inside me. So, as a product manager for Freneo, I would say I am lucky that I am constantly in touch with our customers. I get to learn about their wishes, their feedbacks, in general, how their feeling is, and the ability to transform those wishes and feedbacks into meaningful value additions for our product portfolios and thereby basically contributing to the overall mission statement of Omicron, that we innovate with passion and we take care of our customers. We are detail oriented. We always listen to them. And I think this whole statement, if you look at it in a nutshell, it drives the researcher inside me to look forward to, contributing to more innovative solutions, improving existing product portfolios, and even discover new application areas and so much more.
Well, speaking of application areas, and going back to your wide and broad background, as you mentioned, you started in transformer condition testing and monitoring. Since April 2022, you've been a leading task force at SIGRA, specializing in data-driven modeling of transformer digital twins. Could you please describe your work in this area?
Yeah, that's correct. And yes, absolutely. It's very interesting work, by the way. We all know that power transformers generate vast amounts of data, okay, throughout their lifetime, starting from design data, operational logs, sensor outputs, and whatnot. But often this data are in different formats and different quality levels. And therefore, in a raw form, it's rarely usable. So, extracting meaningful insights from this data requires two things: domain expertise, definitely, as well as the knowledge of which tool, the right analytical tool, which tool to use. And I think in this regard, the condensation of knowledge regarding the data-driven modeling aspects brings a lot of value. So data-driven model helps bring structure to this complexity, by combining historical, event-based, and sometimes even real-time data, depending on what we are modeling, of course. And in the context of digital twins, these models can now integrate artificial intelligence, Internet of Things, IoT, as well as go back to basics, statistics, of course, always, to detect patterns, anomalies, support diagnostic decision making, and so on. So I think industry right now is facing, let's be honest, a gradual loss of experienced expertise. And preserving and translating this knowledge into robust data models is becoming important more than ever. So my work focuses on evaluating different approaches for these tasks, anomaly detection, prognostics, health assessment, with the goal of supporting development of reliable data frameworks for future digital twins of power transformers and to enable advancements in this space.
Very good. Now, just for our listeners who may not be familiar with the term digital twins, could you explain what they are and how they're used in transformer condition assessments?
Oh, yes. The digital twins. Well, this ongoing digital transformation of power systems is creating new opportunities for innovative technologies such as the digital twin. And while digital twins are already in force in other sectors, say manufacturing and aerospace, they are not so common in power industry, although it's a work in progress, disclaimer. So theoretically, digital twins are virtual replicas of their physical counterparts. Okay. And what sets them apart from a typical computer aided simulation is a digital twin's ability to predict and make guided decisions. A digital twin basically contains a data collection layer where the data is collected from all kinds of sources. Then comes an analysis layer where it is filtered, it's modified and prepared into the format that can be used. It's fed into relevant models for whichever purpose this digital twin is being used. And then comes the application layer. After the modeling and analysis, whatever is the outcome, it can be visualized in the form of dashboards or whatever. So there is also this feedback loop which exists between the physical and virtual counterparts. And this feedback allows not only the exchange of real-time data between the two, let me say, parts, the physical and the virtual parts, but also it allows real-time maneuvering of the virtual parts. So the real-time corrections whenever necessary in the modeling and further processing as well. I would say, in simple terms, digital twins turn data into insights and insights into actions. And therefore, in condition assessment, it's a total game changer. It enables early detection of faults, more accurate diagnosis of issues, sometimes even predict failures months before they can happen. So rather than reacting to the problems, operators can make informed, proactive decisions for maximizing the availability of their assets.
Very interesting. Well, thank you for that explanation. Suruthi, do you believe that digital twins will be more widely used in the future? And if so, how and why?
Well, Scott, I think digital twins will absolutely become more widely used. And in many ways, they already are, to be honest. Power systems are becoming very complex. With renewable integration, the aging infrastructure, and the need for increasing reliability, there is always this pressure on the operators that they must have more visibility into their asset. Their decision making should be faster, reliable, accurate, and so on. And I think digital twins provide exactly the answer to these problems by virtually transforming their physical assets. And these virtual representations are evolving with real-time data. So they are not stagnant. They are not based on a bench of data that was derived 10 years ago. And given the strategic importance of power transformers, let's say, this is naturally a priority asset for digitalization efforts and digital twins. And in practice, what this means is we are moving from reactive to predictive operation. So instead of responding to failures, utilities can anticipate issues and prioritize their actions to extend the asset lifetime well in advance, even when the fault is actually in the inception level. And that has a direct impact on the cost and reliability and sustainability goals. I wanted to add that when you asked how this will evolve in the future, I think the answer to that is how it will evolve will depend on the data quality and its integration abilities. And I think with more sensors and IoT devices coming into market, there is this need for the standardized data platform that is available for all digital twins in order for them to become more accurate and more scalable. And at the same time, of course, with the integration of artificial intelligence, we can make these models smarter and easier to use. So I think the future is not just about digital twins, it's about embedding these digital twins into our everyday decision making workflow. And I think that's where the real value proposition is.
Very good. That's very interesting. You had mentioned artificial intelligence. We're about to get to that. So you have a broad area of experience in that area as well. But I want to ask one more question about transformer condition monitoring. At SATA Labs, you were instrumental in digitalizing condition monitoring practices for power transformers. Could you describe what this involved and what you were able to change?
Oh, Scott, we are turning the pages of history book now. Yes, in my previous role in SATA Labs, the focus was purely on the domain side of digitalizing transformer condition monitoring practices. What this means is that I was responsible for the technical specification of the product design, and the product itself was an AI-driven solution for responding to transformer asset health assessments. And the idea actually was very simple. It was to develop a product that colleagues who don't have that high level of expertise in asset health management and assessment and risk analysis and so on could use for their immediate, let me say, overlook of their actions and how to plan the next steps and so on. So it was built in an order where we can help at the very grassroots level, and it was not meant for top executives, but for the person who was standing in front of the transformer. And also for those who are not very educated on artificial intelligence and machine learning algorithms and often think that this is all a black box technology, to help them simplify this workflow of how things are being interpreted and forecasted and resolved and so on. I was mostly focused on that.
Suruthi, the use of artificial intelligence in power system testing is another area you have been and continue to be involved with. I noticed that in a recent LinkedIn post, you wrote, quote, "I would say we need to get over the AI infatuation if we are only using it to confirm human predictions," end of quote. That's interesting. Suruthi, in your view, what is a better use for AI in the power industry today?
Oh, Scott, you have made a home run. I think there's one more part to it. That's a very personal observation, I would say. I think most of us, irrespective of our industry, we use artificial intelligence for summarization tasks. And artificial intelligence is far more than just ChatGPT or Copilot. I'll tell you something interesting. You do a quick Google search and you type, where is AI being used the most in power transformers? And two places that will come up are maintenance planning and fault prediction or fault forecasting. I'll give you an example. We have been using artificial intelligence models for fault prediction in power transformers, even fault classification of transformers in larger fleets, based on dissolved gas analysis, the DGA data, for instance. And the rules and the relationships between gases and faults is often well defined, okay? Therefore, we are using artificial intelligence to validate what we know and instead of using it for discovering something that we do not know. And that's what I meant. In my opinion, what would make a nice use case for artificial intelligence is to use it for extracting behavioral patterns of gases from the dissolved gas analysis data, but by combining those gases that have not been explored before. And I think this enables us to foresee a faults months before it will happen. And this will be a new area altogether. Another similar strategy for artificial intelligence, in my opinion, to identify complex fault developments would be oil degradation, for example. We know that oil and paper insulation inside a power transformer degrades over time due to the presence of oxygen pressure and temperature. And it triggers a lot of chemical reactions. Sometimes these reactions are very complex. But what very few people probably know is that definite reaction kinetics, a rate kinetic equation for this degradation mechanism, cannot be developed because either it's too fast or it's happening simultaneously. It's not very clearly known. We know what reactions happen, but in which order exactly, nobody can set it on stone. I will say this publicly. And therefore, I think AI, this is a wonderful place for AI to explore, If artificial intelligence can help us explore and explain what is the exact sequence in which these reactions occur, instead of saying broadly these are the reactions that happen, help us define a rate kinetics, then we can maybe improve our degradation models as well. So I think this is why I keep saying that we need to use AI for better things and not confirming what we already know.
So it's a very good point. Where do you see AI having the most immediate impact in the power industry? Predicting when a system will fail, enhancing the accuracy of real-time testing procedures, or is it, in your opinion, something else?
That's a very interesting question indeed. But I think it's a combination of many things. With artificial intelligence improvement, predictive maintenance will certainly flourish. There's no doubt in that. But that's only one part of the story. The other part would be to have more visibility into the asset. And think of this, as I mentioned before, as artificial intelligence driven digital twin of a power transformer, and by extension, that of a substation. We can have far more visibility towards an asset's lifetime. Based on its strategic significance, we can make informed decisions. Even the smallest of plannings could be faster, more efficient. And then I think this would be a game changer for grid operators, especially those who are focused on interoperability, like in Europe. Let's put it this way. So I think it's a combination of a lot of things. And there is not one area only. This, from the design of the transformer to commissioning to the everyday operation and so on, we have so much more to explore. So yeah, definitely looking forward to that.
Very good point. How do you ensure that field technicians and engineers can trust AI-driven results without losing their own critical diagnostic skills?
In my opinion, I will give my secret mantra. So yeah, it's, in my opinion, learning, testing, and adapting. This is my secret mantra for everything, not just AI. I think we certainly need a basic level of education among technicians and engineers about what artificial intelligence is, what are its capabilities, what it can do for you, and so on. But at some point, we need to educate them so that they can understand just because data exists doesn't mean you need artificial intelligence for it. So, this decision making of when to bring AI into the picture comes with learning. And I think there should be the first step for us.
Very good. How do you perceive people actively learning? That requires a bit of discipline, wouldn't you say?
Yes, of course, a bit of discipline and, of course, a bit of indulgence. Open-mindedness is also something that, you have to take it with a pinch of salt. Because until and unless you don't make your mind open, you allow yourself to come into this, push yourself out of this comfort zone, you won't be able to pick it up. And at the same time, it's also important that people understand that AI is not algorithms only. It's not just algorithms only. There's a basic science behind it. So instead of being afraid of that science and imagining it just to be a black box thing that nobody can touch and nobody knows what's going inside, step-by-step learning, basics of what is AI. If you are talking about machine learning algorithms, what is machine learning, first of all? What are these algorithms and what is the mathematics behind it? Once people start to understand these things, it really makes a change for those developers who are doing AI-based developments, let's say, for them to explain the outcomes of their models. So I think let's push ourselves out of the box.
Very good point. Now, coming to another area where you are currently involved, a path you're currently on, is power quality analyzer testing as a product manager. Suruthi, as a product manager for PQ analyzer testing, you focus on verifying the accuracy of these devices. Why is the testing of the tester so critical in today's increasingly complex decentralized grids?
That's a great question. See, Scott, I think power quality, or PQ as we say it, testing current transformers is especially important in decentralized grids because everything depends on accurate current measurements, right? So, current transformers are essentially the eyes of the grid, and they help detect all kinds of issues: harmonics, voltage, disturbance, load imbalances, you name it. So, they play a very critical role in rapid, quick identification of faults and isolating problem areas. As grids are becoming more complex and there is this integration of renewable energy happening, their role is becoming even more critical. So I think not just because they help make reliable measurements, but you can't ensure stability, efficiency, or even a smooth transition into sustainable energy systems without power quality measurements. So I think that's where the focus of these power quality analyzers are from our perspective, from Omicron Electronics perspective.
Very good. So the rise of renewables and electric vehicles, for example, power quality is more volatile than ever. How have the parameters we need to verify in PQ analyzers changed over the last decade?
You know, Scott, you are quite right. PQ analyzers have evolved quite a lot in the last decade. And the evolution is obviously very significant with the rise of, as you mentioned, renewable energy as well as the introduction of electric vehicles in the market. Because mainly it has made the grid more dynamic, in my opinion. Today, we don't just measure basic parameters, okay? We capture voltage fluctuations like flickers, which are caused by solar and wind variability, a major, let me say, presentation from the renewable integration part, or even harmonic distortions, which generate from inverter based systems, such as using metrics like total harmonic distortions and even frequency isolations due to intermittent generations. And these come into picture with the evolution and with the introduction of these additional concepts into the grid. So PQ analyzers also monitor reactive power imbalances as well, which are increasingly important for maintaining grid stability. And I think overall, PQ analyzers are becoming more sophisticated in reflecting the need to manage a more volatile, decentralized energy system while ensuring reliability, sustainability, efficiency, and security.
Very good. Now, with all the paths you've been on before, transformer condition assessments, AI, and now power quality, at some point these paths intersect. Do you feel that you've reached that intersection? And if so, what are you noticing when all these paths meet?
Oh, I must borrow a line my lovely husband tells me every single day. He says, learning is an everyday process. So when you asked Scott, have I reached there? I don't think I will ever reach there because learning is an everyday process. So I'm every day learning something new. But I would say that they do cross, they do cross because I think at some point, the basics, the fundamentals, they never leave you. It's just we forget about them in the ocean of everyday things, but someday when it hits you and you realize, oh, wait, you pause, you take a pause, and then you look back. Hey, I have read about that. I have learned about that in school. So maybe just open my textbook and take a reference from there and solve this problem. So I think it would be a lifetime before I can say in confidence that, oh, yes, I have reached. But the intersection is on my horizon and I'm moving towards it every day.
That's a great outlook. Suruthi, looking forward, if you were advising a young engineer entering the power system testing field today, what non-traditional skills like data science or AI should they prioritize along with their electrical engineering fundamentals?
That's a very good question, Scott. But I think there are already many great courses of basics of data science, artificial intelligence, and so on. If you ask me where my opinion lies, I would say go back to mathematics. I love mathematics. I love the possibility of translating something into a beautiful equation. And it becomes all the more beautiful when you can solve it. So, artificial intelligence, as I said previously as well, is nothing but pure mathematics. Things that we forgot that they existed or never cared about them so much to pay attention. For example, regression models. I think each one of us at some point in our lives have studied curve fitting into our mathematics classes. But now, when it comes to the same regression models driven by artificial intelligence, we sometimes question the outcome. How did it happen? Is it hallucinating? Is the AI hallucinating? Can we explain? And so on. I always say go back to mathematics. If you can't explain this with AI, go back to mathematics, see where you can explain there or not. So, go back to basics and everything will start making sense. That's what I would say.
Good advice. From your perspective, what will the future of the power industry and power system testing look like?
Oh, that's a very good question. I think we are looking at a very interesting landscape of 3Ds: decarbonization, decentralization, and digitalization. Regulating bodies need to speed up. They cannot spend years on deciding how to build a standardization strategy for certain testing aspects, because the energy landscape is shifting fast. The market requirements are shifting fast. And they need to be quick on their feet as well. At the same time, how key stakeholders adopt these approaches and adapt themselves with the changing regulations will finally tell us how the future would be for the power industry in general. And I would say that a fantastic way of learning this entire outlook was from my experience from the PQ analyzers and the development of power quality testing solutions and releasing them in the world.
Suruthi, thank you so much for joining me and my listeners for this episode of Energy Talks and sharing all of your wonderful insights into power system testing and your major areas of involvement. So thank you again.
It was my pleasure, Scott. Thank you very much for having me. I really hope that our audience enjoys this podcast and this conversation. So thank you very much.
Well, thank you again. And a big thank you to our audience for listening to this and other episodes of Energy Talks. We always welcome your questions and feedback. Please send us an email to podcast@omicronenergy.com. Omicron has several years of experience in power system testing, data management, and cybersecurity, and offers a matching solution for your application. For more information, visit our website at omicronenergy.com. Please join us for the next episode of Energy Talks. Goodbye for now, everyone.